Welcome to the fifth and final part of the module on economic and hydrologic modeling. In the previous parts of this module, we looked at how models can help us understand complex processes in the real world. In this part, we're going to see how models can help us analyze water management policies as well. Recall that in parts 2 and 3 of the module, we built the farmer profit equation, starting with our understanding of what a farmer's production decision is like, simplifying it, picking some variable names, and writing out the equation for profit. In part 4 of the module, we discussed the glover-balmer equation, which helps us estimate what the rate of stream depletion is given the rate of groundwater use at a well and different characteristics of that well. How can these equations help us look at policy questions? So let's start with the farmer profit equation, which I display here again. One policy question that we can answer thanks to this model is the following question. If a regulator decides to pass a law so that the farmer cannot use more than a certain amount of water, say W sub R gallons of water, will this decrease the farmer's profits? And if so, by how much? This could be an important policy question because it shows us that there are trade-offs. There may be trade-offs in a regulator's decision to limit water use by the farmer. The regulator may want to limit a farmer's water use because there are environmental benefits to using less water, but this reduced water availability for the farmer may lead to a decrease in farmer profits. So if that is the case, it would be important for the regulator to know how much those decreases in profits would be. We can estimate what these changes in profits would be by using our model, the farmer profit equation. We can take this equation and find the farmer's profit maximizing level of water use, as we did in part 3 of the module, and compare it to W sub R. If W sub R is greater than the farmer's profit maximizing level of water, then the farmer's profits will not go down if the regulator decides to impose this limit on water use. However, if W sub R is less than the farmer's profit maximizing level of water use, then the farmer is only going to be able to use an amount of water that is less than what he would like in order to maximize his profits. How much is a water use limit of W sub R going to hurt the farmer in terms of profits? We can again use this model to help us quantify that. We can calculate what the profit of the farmer is if he uses his profit maximizing level of water use, and then we can plug in W sub R into this equation, the profit equation, and figure out what the profit is for the farmer if he only uses W sub R units of water, which is what the regulator would allow under this rule. And so then you have profits that are under profit maximization for the farmer and profits that are under this law where the farmer can only use W sub R gallons of water. And you can compare those two profits in order to see what is the loss to the farmer in terms of profits due to the regulator passing this law. Another policy question that can arise is if we think about a policy in which the regulator decides to charge a farmer a fee for each unit of water that the farmer pumps. For example, the fee could be some level C sub F. This kind of policy establishes a price for groundwater, a price to the farmer for the groundwater, in addition to the cost that the farmer already needs to incur in order to pump the water out of the ground. So the policy question is, how will the introduction of this fee change the farmer's profits? Well, again, we can figure that out by adding this fee to the variable costs that the farmer needs to pay in order to pump units of water. What you would do is, instead of just C sub W, now you would have C sub W plus C sub F here. Multiply that cost by the amount of water used by the farmer, and that will give you the total cost to the farmer of pumping those units of water. By introducing C sub F into this equation, you can then, as we did in part 3, take the derivative of this profit function and see what is the profit maximizing level of water use for the farmer, given that he now also has to pay a fee for every gallon of groundwater that the farmer pumps. So, in summary, this model also allows us to address policy question number 2, which is related to a policy in which we are now going to charge farmers a fee for every unit of water that they pump. So those were 2 questions that we could address using the economic model. Now let's turn to the hydrologic model, the glover-balmer model. What is a policy question that we can answer with this? One policy question is as follows. If a regulator wants to keep the rate of stream depletion below a certain level, say V sub R, during the next year, what groundwater pumping limits should he impose? How does the glover-balmer equation help us answer this question? We know that the regulator wants to achieve a level of stream depletion V sub R. So we can plug in that value V sub R here, where the rate of stream depletion goes in the glover-balmer equation. And then if we have information on the well, specifically the distance of the well from the stream, the storativity of the aquifer that the well is pumping from, the transmissivity of the aquifer that the well is pumping from, and we know that we're talking about stream depletion over the next year, so capital T here would be 1 year. Then we have values for V, D, S, tau, and T, and so we can solve for U, which is the pumping rate that the well with these characteristics can pump at so as to keep stream depletion at a level V sub R. So thanks to this model, we have been able to would be able to answer this policy question, which is, if we want to achieve a certain standard of the stream depletion, how should we regulate the well? What pumping level should the well be at? Now, we can also use both the farmer profit equation and the glover-balmer equation together to answer other kinds of policy questions. For example, policy question number 4. Suppose that a regulator wishes to limit a farmer's groundwater use in order to keep the rate of stream depletion below V sub R during the next year. What will be the impact of such a policy on the farmer's profits? Okay, so here we are in a situation where The regulator wants to limit the farmer's groundwater use, and the goal for the regulator is ultimately to achieve a stream depletion rate of at most V sub r. So how would you answer this question using our economic and hydrologic model? Well, using the glover-balmer equation, as we explained in the previous slide, we can figure out if we want to achieve V sub r, we would plug V sub r in here and solve for the level of U that would give us that V sub r, assuming that we know all of the characteristics of the well. Once we have the rate of groundwater pumping, then we can think about a certain period of time and translate that rate of pumping into a quantity of water. And we can then plug in that quantity of water into the farmer profit equation in order to calculate the farmer's profits. Those would be the farmer's profits that would result from having a level of water use that would achieve stream depletion V sub r. And we can compare that level of profits to the farmer's profit maximizing level of profits that he would be able to achieve if he were not subject to this regulation where stream depletion must be kept below V sub r. In this last policy question number 4, we used both economic and hydrologic models at the same time. We used both the farmer profit equation and the glover-balmer equation in order to answer the policy question. And this is an example of something known as integrated assessment modeling. In integrated assessment modeling, a researcher develops a system of models where models from 2 or more academic disciplines are integrated into a single framework. In this case, the 2 academic disciplines were economics and hydrology. Integrated assessment modeling can generate useful information for policy making, as we saw in the previous example. So to summarize this last part of the module, using the farmer profit equation and the glover-balmer equation as examples, we have shown how economic and hydrologic models can help us answer questions about water management policies. So these models really do help us try to figure out how to manage our water resources better. We have also learned how we can use these models from different disciplines, economics and hydrology, together to help us answer policy questions. And we've learned that such an exercise is known as integrated assessment modeling. This concludes the module on economic and hydrologic modeling. I hope you were able to learn something useful. Thank you very much for listening.